Okay, quadratic functions. Okay, there's now today I want to talk. I'm going to kind of take how we can quickly graph quadratic functions. We're talking about the graphs of quadratic functions. If we have time, I want to maybe show you some features on your calculator that are very helpful with quadratic functions. There will definitely be, I want to break chapter 5 up into 2 parts too. We'll break halfway through the chapter and do a graphing and non-graphing test, and then we'll finish up the chapter and do a second one. There's going to be a real big, Joey, why don't you get rid of that stuff? Let's get all distractions away here. Definitely be a big graphing and non-graphing component on this thing. The graphing component is really going to be just knowing how to use that tool to analyze quadratic functions, okay? So quadratic function in what we might call general form or standard form. It's called both. I think the newer books tend to call it general form instead of standard form. But it really is, that is standard form. As we'll see next chapter, it's really just a polynomial in standard form. It has this form. Okay, so y equals ax squared plus bx plus c. And in order for this to be quadratic, a can't be 0. Because if a is 0 and that first term goes away, what is that? That's just a linear equation then, right? It's just a line. Okay, so we'd say that this is what we call the quadratic term, and a is the quadratic coefficient, because that's the term that makes it quadratic. Okay? All right, so we know, and you've seen these things before, right? You have done some stuff with quadratics before, probably just not a lot. We know that they're U-shaped graphs called parabolas. That's what the graph of any quadratic function always looks like. It's a parabola. Now they can be tweaked. They can open up or down. They can be, tall and skinny or wide, and they can have all kinds of shapes. But they always have that characteristic shape. There are some interesting things about parabolas too. If anybody have satellite TV or satellite internet or something like that, or you know what I'm talking. If you've seen any satellite dish, that is parabolic in shape. Now it's a pretty wide parabola. It's not a real deep, narrow one, but it's a parabola, and the reason for that is there's some characteristics of a parabola that are really important in optics and in fields and waves and in electrical engineering. Primarily this, that there's a point that we're not going to talk about parabolas in this way right now, but I hope at the end of the year to come back and look at what's called analytic geometry and revisit the whole concept of a parabola from a little different perspective. And there's a point for every parabola called the focus or the focal point. And anytime
light wave,
exactly, any light waves coming in, any kind of any electromagnetic wave. It doesn't have to be light. It could be a radio wave. It could be a microwave. It could be anything that comes in that's reflected off the surface of this parabola, goes through, and even down here they'll bounce around and go through that point. They all go through that focal point. And that's why when you see a radar dish, there's always that little dongle that hangs out over the middle. That's the receiver. The whole dish part is just to reflect everything through that receiver. And so that's why they're so good at that. That's why when you have satellite TV, you've got this great big, this reasonably large dish that's intercepting a lot of incoming waves, but they all get focused through that tiny point. Yes, sir?
I thought that the dishes, when they dig, they're just part of a circle.
No, they're not. They're not part of a circle. And that's what makes them a little bit more expensive to make, is that they're part of a parabola. If they were part of a spherical cutout, it'd be easier to make them. But they're not. They're parabolic. And then you can reverse that too. If you wanted to send a signal up to the space shuttle or something that's really far away, if you wanted to do that, wouldn't you agree that you couldn't just send some signal that's going to get diffuse as it gets further away? If you tried to shine a flashlight up at the space shuttle, they're not going to see it because the flashlight is going to disperse, right? But if you reverse this process and you generate the signal at this antenna inside the parabolic dish, and really what you want to do is shoot it down more than up. And then as this signal gets bounced off the parabola, it reverses the direction of these rays, and they all go out parallel. And so they end up they're very collimated. We call that in physics. They keep the beamway stays about the same the whole way, and they just, travel straight up towards the space shuttle, it's gonna disperse a little bit, but that's okay, it's not dispersing massively, covering thousands of square miles. And so you can track that thing, you can point the dish right at the space shuttle and have very good communications, for example, right? What was I gonna say about that? Something just popped in my head to say about that too, I can't remember what it was now.
Is that why like some flashlights have like, they don't always like shine out, they have like a little thing and it goes out?
Right,
towards
they
the
do,
thing?
they do, and what happens is, typically with a really good flashlight, like the ones that you can, the really bright ones that can shine in a very narrow beam, what you're doing when you twist that thing and you can kind of adjust the beam, all you're doing is you're just moving the light bulb vertically up and down relative to this parabola. And so when it's right in the exact focus, it's gonna send that light out in a very narrow beam. But when you move it up a little, I don't know if you're moving it up or down, either or would work, it takes it away from that focal point, and then the beam starts to spread a little bit. Okay, does that make sense? And it's, that's kind of just interesting. Parabolas are, for that reason, they're really interesting, shapes for us. But we're gonna look more at the mathematical part of that now. But if anybody's got an interest in, and I hope you do, in going on in engineering or physics or something, you're gonna see a ton of these guys. It's a really important shape. Okay, so, moving on. The highest or lowest point down here is called the vertex, right? And as we're going through this, in your mind, kind of make a connection to maybe the absolute value formula, or the absolute value functions we looked at earlier, which were V-shaped, right? Same concept, only instead of a V, this is a U. But you'll see here shortly that the way we talk about parabolas is highly analogous to the way we talked about absolute value functions. It's slightly different, but it's really similar. So this is the vertex, kind of the point of the U, if there is a point, the very tip of the U. And there's some characteristics of these guys. Okay, for one thing, you can see right now that they are symmetrical about a center line, aren't they? If we draw a vertical line through the vertex, that's the axis of symmetry. And so we could fold them over on themselves or reflect them on themselves, and they would overlap perfectly, right? I could, with a wet ink, I could start at the vertex and graph one half of this thing and just fold the page along that center line to make the other half, right? So that's the axis of symmetry. We know that parabolas, and you probably already know this, parabolas open up if they're multiplied by a positive number, and they open down if they're multiplied by a negative number, and that's pretty standard. We've talked a little bit about this stuff earlier, about just for all functions. Same is true for absolute value functions, right? What else? Okay. Let's see about. Question?
Could you replace the X with the Y so it's X equals
You could.
Y?
You could. And what do you suppose would happen if you did that?
Equals sideways.
You go sideways. Yeah. You can have sideways parabolas. You can have parabolas that are tilted in any direction. Our focus in here, being as this is kind of, later on you'll do more of that stuff. Function rotations and transformations. And really what you're doing, if we remember, whenever we trade the X's and Y's, all that just amounts to an inverse of the original relation, right? Swapping X and Y just gives you the inverse, and the inverse is always the one that has symmetry about the line, reflective symmetry about the line Y equals X. So let me, good question. I don't want to brush that one off. Let's take just a quick, let me give that a little more attention than the book does. So for question? Yep.
If it is sideways, would that not be a function?
Say it again.
If it was sideways, like.
You're right, it wouldn't be a function. It wouldn't, it'd violate the vertical line test, wouldn't it? Yeah. It'd just be a relation, but it still would be the inverse. So if this is our original parabola, okay, that one is a function, isn't it, right? If I were to, so this is y equals x squared. If I swap the x's and the y's, then that's how we create the inverse, and that's going to have reflective symmetry about that line y equals x. Okay, so if I write instead x equals y squared, we're just going to take this thing and reflect it around that green line. it's hard to see. Remember, I had a trick for you for that. It's a little bit hard to do that visually, but you can always find the graph of an inverse. You can trade that one kind of tricky reflection for two very easy ones. If we rotate the parabola 90 degrees about the origin, right? So in this case, it's going to rotate over there and then reflect it over the y-axis. Those are two easier steps that I think it's a good trade to make for that one step of reflecting it over that diagonal line, right? Either way, you're going to get this, aren't you? Okay, so you're right, it's a non-function, but it is the inverse relation, right? Make sense? Okay, good question. So the origin's the vertex of both of these guys. Y-axis is the axis of symmetry, okay? So graphing a quadratic function. Now this isn't the order that I would choose to present this in, but it's not a big deal. So if we're given a quadratic function in general form or standard form, how do you graph it? Well, here's the important equation. Well, first of all, we know that if A is positive, it opens up. If A is negative, it opens down. The bigger the absolute value of A is, the more that it's stretched vertically, right? So if the absolute value of A is greater than 1, then it's stretched relative to our prototypical y equals x squared parent function. If the absolute value of A is less than 1, it's going to be shrunk and widened, right? Okay. A good way to, well, I'm not going to say it yet. We'll talk about it when it comes up. The x-coordinate of the vertex, this is the important equation right here. This is really all you have to remember. The x-coordinate of the vertex has this value, the value given to us by this little expression, negative b over 2a. And if you can find the x-coordinate of the vertex, the rest is pretty simple. If I know the x-coordinate of any function, how do I find the corresponding y-coordinate? So just as an example, say we had some quadratic function and we knew that the vertex was at x equals 3. How would I find the y value? Plug it in. Yeah, just evaluate the function at that x value to find the corresponding y value, right? And then once I know the x and y coordinates of the vertex, that's how I anchor the parabola. That's my starting point. And then really most of the time we're just sketching it anyway. And so if A is positive, we just know we're going to sketch a parabola that opens up. If A is negative, we sketch a parabola that opens down. If we want to be more specific, we can pick a couple test points on either side, like this. Okay. So in this case, can we all identify the values of A, B, and C there? Right? A is the code, so A would be 2, B would be negative 8, C would be 6. So then we know it's going to open up. What is the x-coordinate of the vertex going to be? And maybe just what's the formula? You remember? Oh, negative b over 2a. Good. So it's going to be 2, isn't it? So we get negative b. Well, if b is negative 8, then we're going to get positive 8, aren't we? Negative times negative is positive. Over 2 times a, well, a is 2. So we end up with 8 over 4 is 2. There's the x-coordinate. I can find the y-coordinate by just evaluating the function at x equals 2, right? And if I do all that, I get negative 2. That's no big deal. So those are the coordinates of the vertex then. Positive 2, negative 2. Okay? So let's add the vertex. Now we know that it opens up, and our axis of symmetry goes vertically right through the vertex. What do I need to do to get a sketch of this thing? You know, like I say, most of the time, we don't need to be more specific, really, than just where is the vertex and does it open up or down. If we do need to be more specific, and we're doing a sketch, because this is really just a sketch. If we want to do a really accurate graph of a function, what are we going to do anyway? I mean, we're just going to punch it in our calculator and write, or put it on a computer. I mean, there are ways that we can graph functions accurately if we need to now using technology that really it makes this pretty obsolete. But a lot of times we want to just do a quick sketch of a graph that's good enough. So we could pick a couple points on either side of the test points on either side of this axis. For example, if I know that the vertex has an x value of positive 2, what would be some good candidates for X values that I could plug in to find some test points to kind of guide my sketch a little bit? Would I, for example, want to pick an X value of -4 or +10? Something close to it. And that's especially important with parabolas because parabolas accelerate. The further you get away from the vertex, the more steeply it climbs, or the more steeply it drops, right? And so you don't have to go very far away from that center line, from that x equals 2, to get really large or really large positive or negative y values that are hard to graph. So we really want to stay, does that make sense when I say we want to stay pretty close to home when we're picking our test points? We want to be right around that x equals 2 value. So maybe just go 1 to the left or 1 to the right. And in this case, which would be easier to do? We always like to deal with numbers that have smaller absolute values because they're easier to make computations with. So do we want to go to the left side or the right side here? Probably the left side. Yeah, why not pick values that are close to 0, right? So if I pick, like, for example, x equals 1 and x equals 0, and they pick 2, let me just pick 1. 1's plenty. 0 would be an easy one, wouldn't it? 0 is always the easiest point to pick. If I plug 0 in for x, what do I get for y? 6, yeah. So if I know I'm getting the point 0, 6 on this side, and it has that reflective symmetry, this is always a 2-for-1 deal. If I know I get that point, then don't I also know I'm getting the corresponding reflected point over here, right? So, they say plot 2 on one side, I say just 1 is sufficient. There's the kind of the cousin point of this one. And then just connect the dots with a parabolic shape. And there's your sketch. Does that make sense? Okay. All right, so that's standard form. Ironically, that is the hardest one to graph. The other two forms that we typically use are much, much easier to deal with. Vertex form is a really useful form. Now that looks awfully familiar, doesn't it? Right? Compare that to the absolute value stuff that we did earlier. Right? For an absolute value function, didn't we say that the parent form, that what we called it vertex form, was a times the absolute value of x minus h plus k? Really similar, right? We've got a power of 2 in this one, and we have parentheses instead of absolute value bars, but very similar. And then the key difference is this gave us a V shape, and this gives us a U shape. But the meaning of those things is still the same. The h and the k are telling us the coordinates of the vertex, and the a is telling us the same thing it did in the last example. It's telling us if it opens up or down. Okay, make sense? Okay, so these are very simple to graph. If I'm given a quadratic function in this form, that's all I need to know, right? There's the vertex. A tells me it opens up. Pick a test point on one side or the other, reflect it, and you got it. Okay, intercept form, or sometimes it's also called factored form. I prefer to say factored form, but the book says intercept form. That's fine. This is what it looks like, okay? A times the quantity x minus p times the quantity x minus q. And very shortly, we're going to start practicing factoring quadratics, and this is what our result looks like after we factored. In this case, we know that the places where y equals 0 what are those going to look like on any function? Where y equals 0, what's happening to the graph? If I draw a little coordinate plane up here, there's my y-axis. When y is 0, what's happening? No, something important is happening. If this is, for example, my parabola, what's unique about the places where y is 0? They're the x-intercepts, aren't they? Right? So the places where y is 0 are always going to be, we call them zeros or x-intercepts, but they mean the same thing, right? That's where it's crossing the x-axis. Okay, very important points. The point of writing a quadratic function in this factored form or intercept form is that we can use what's called the zero product property. We know that if I have a product of a bunch of factors, let's do a little warm-up here. Okay, I don't know if I did this to you guys or not, but let's do a little warm-up real quick. If we, if we multiply some numbers together, I want you to tell me the answer. Just get your brains working a little bit here. So let's multiply 10 times 2. You just do this in your head. Times 0.5 times 0.7139. Okay, times pi. Times Google. Okay, times 0. Okay, it's 0, yeah. As soon as I multiply by 0, no matter how complicated the other factors were, the answer goes to 0, right? That's the concept behind the zero product property. If I have a product of factors, the value of the product is always equal to 0 when any one of the factors are 0, right? And so if I write my quadratic function in this form, I know that where any piece of this, where any individual factor goes to 0, the whole function is going to have an x-intercept, right? Because the y value will be 0. And so if I want to sketch a graph of a function in this form, it's really easy to do. I know that the x-intercepts are going to be at the values of p and q, right? Because those are the values. If I put in x equals p, I get a 0 there. If I put in x equals q, I get a 0 there, right? Yes, sir.
What if your parabola doesn't cross any sometimes?
It might not. It might not cross. If it doesn't cross the x-axis, then you can't write it in intercept form. I mean, if you do, what's going to happen, and I don't want to, this is kind of strange, you're going to get i's in your answer, which are imaginary numbers, but we haven't gotten to that yet. Okay. But you would never write it that way. Here's an example of one where it doesn't cross the x-axis. You could come up with one too. Y equals x squared plus 5. You can't factor that. Okay, so that's, you just have to just leave it like that. Okay, good question. So all we have to do then is to get to graph one of these guys. Instead of starting with the vertex, we're starting with our two our two cousin points, which are the x-intercepts. We just graph the x-intercepts. And we know that the axis of symmetry has to be halfway in between those, right? Because they have to be reflections of each other. And so the x-coordinate of the vertex then must just be the middle value or the average of those two numbers, p and q, the x-intercepts, right? So for example, if the x-intercepts, if we know that our parabola is crossing the x-axis at say 2 and 10, what is the x-coordinate of the vertex, which we could call h? Yeah, it's going to be 6. How do you get that? Add them and divide by 2, right? That's how we always find the middle value, or the average. Okay.
We're gonna have to mind our P's and Q's.
You are going to have to mind your P's and Q's. Yes, you are. Okay, and like always, the A means the same thing in all three forms. Okay, so let's look at a couple quick examples. If we wanted to sketch a graph of this one, that's in vertex form, right? What's the value of A? -1/2. What's that tell us? Opens down. Okay. What are the coordinates of the vertex? No. No, because say it again. -3, 4. Good, because this is like it was with that. Remember how that's a little strange at first with the absolute value functions. The value of h is the number that is being subtracted from x, right? And so in this case, x plus 3 is equivalent to x minus -3, right? So it's always going to be the value of h is going to be opposite of that operation, the sign of that operation, right? So h is -3, k is obviously 4, right? So where's the vertex then? -3, 4. Good. Okay, so there's our vertex, right? We know we have axis of symmetry just goes right through the middle. And then we're just going to pick some points. Now you want to, I mean, it'd be nice to pick points that gave us non-fractional answers, right? So you got to kind of be a little bit sophisticated here. You can't just randomly pick a number. In order for this to work out, for us to not get a fractional answer when we're multiplying by 1/2, what has to happen with this expression right there? It has to be even, right? So it'd be nice for us to pick an x value that's going to give us back an even answer, wouldn't it? Right, so for example, picking, like 3 would be good, wouldn't it? Something like, well, hold it. Yeah, 3 would work, but 3's pretty far away. Pick one close to it. 1 would work, wouldn't it? Yeah. 1 plus 3 is 4. 4 squared is 16. That's a good choice. Picking 2 isn't quite as good this time. If I pick 2, I get, or -2, I'm sorry. If I pick -2, or really -1 is the one we want, isn't it? Probably -1 would be good, because -1 plus 3 is 2, squared is 4. Picking -2 is giving us back 1 squared is 1. I'm getting a fractional answer, right? So we'll pick instead -1. Okay, and they graph 2. We could probably get by with just that 1. That's all we really need. Reflected over the axis of symmetry to get the cousin point. Connect in a U shape, and there's your sketch. Okay, no big deal. Okay, we got one in factored form or intercept form. What's the value of A? -1. What's the first x-intercept? The value of P? -2. Value of Q? Okay, so then we know that those are our x-intercepts. -2 and +4. And they're symmetric about that center line. So what's the x-coordinate of the vertex going to be? +1. If I average -2 and 4, -2 plus 4 is 2, divided by 2 is 1. So 1 is the x value. All right, now how am I going to find the y value? How do I always find the y value? I know an x value. Plug it in. Yeah, plug it in. So plug 1 in for x. And if I plug 1 in for x, I get -3 times -3 is +9. Right? So my coordinates of the vertex then are +1, +9, and it opens down through those 2 points. Done. Does that make sense? Okay. So we can obviously, we can use algebra to transition between these things. And this is where probably, I'm not gonna have to spend a lot of time with you guys. Your algebra skills are so good that this is gonna be a piece of cake for you. Like if I wanted to go, for example, if I had a quadratic function that was in factored form and I wanna put it in standard form, I'm just gonna distribute. You can call it FOIL if you want to, but really, all it is distributing. FOIL is, I have kind of a love-hate relationship with FOIL. It's a nice way to remember how to do this, but FOIL it only works for binomials. And we're gonna very shortly, when we get to chapter 6, we're gonna be expanding big polynomials times big polynomials, and then FOIL is insufficient. So if you just remember that you're always just distributing the terms from one of the factors into the other factor, that's how you do it, right? So if I distribute the x from the first factor to the second factor, I distribute what I would probably do, I mean, that's fine. So I'm really distributing the x from this factor into both parts. No, I'm not. Distributing the x from the first one, sorry, that's fine. Then I distribute the 3 into both parts and just add up like terms, right? I mean, that's just no big deal. And you can remember FOIL if you wanted. It's just distribution. Okay. If we wanted to reverse that process.
FOIL's good for distribution and protecting the plane waves.
Yes. True. And if I wanted to, what if I wanted to go the other direction? What if I started with a function in standard form or general form, and I want to go from here to there? Do you have any, remember how to do that?
They have that 2 numbers like that, add together to equal 8 and multiply together to equal 15.
Yeah, and that's what we're going to talk about next section. That process is called factoring, right? That's harder to do in general. The process to go from here to here is called expanding. That's easy. That's just distributing. Going this direction is factoring. How would you go from, say, oops. How would you go from here to standard form or general form? What would I do if I wanted to write that in ax squared plus bx plus c form, general form? Yeah, good. I'm gonna simplify. And the point I want to make here is that with any function, if you just simplify it, you always end up with what we call general or standard form. Okay, so in this case, we'd have to follow order of operations, right? If we're simplifying, whoops, hang on, thinking foil. Simplifying is that direction, right? So we can't do anything in the parentheses, but we can square this out first, right? We have to square out x plus 3, get an answer. Then we would distribute by multiplying, we distribute the 2 all the way through that answer. And then finally, we would just add up and subtract like terms. Okay? Yeah, so we get,
My brain is wrong.
yeah. And we'll learn some of those patterns, but there is a pattern for multiplying out binomials. I'll show it to you now. I'll give it to you officially later. It just looks like this. Maybe you've seen this. A plus b squared always just expands into a squared plus 2ab plus b squared. Okay. But you can also, for now, if you don't remember that or you haven't seen that, x plus 3 quantity squared just equals x plus 3 times x plus 3 and just FOIL it or expand it, right? Okay? Real quick, maybe I'll show you something on the calculator. That's probably good. We got a lot of stuff there.
My brain's
Yeah. Now, what I'm going to do on these assignments, for your benefit, I'm gonna break these up into pretty small pieces. Like I'm gonna give you an introductory assignment on just vertex form. Right? I'll give you a short introductory assignment with very few problems on just general form, and then a short one on factored form. And then at the end, we'll give some practice on those, and then I'll probably give you one kind of extension assignment with some harder problems on each of those. But I'm going to try to break it up into small pieces. It seems like that'd be helpful to not have kind of smaller stuff that you can. Questions get limited to one assignment a little bit more that way. But you tell me if that's not a good idea.
I have the idea why I like it.
So, no, good point. Okay, so a couple things here. If we take a just a parabola, I'm going to get out of inequality. What happens, by the way, while we're in inequality? What do you suppose it looks like if I do an inequality that's quadratic? What do you think? Let's try that. So what if I did, for example, y is greater than x squared? What do you think I'm going to get?
It's gonna be
Make sense? Okay. This time, the boundary is not a line, it's a parabola, but it's the same concept. We're either going to always shade above or below the boundary. And so instead of calling it a boundary line, we call that an envelope in math lots of times. This is shading above. Now what if I flip the inequality around? Let's do alpha less than or equal to. So now it becomes, if it's less than or equal to, it becomes solid. And where am I going to shade? I guess maybe I didn't get it to I left it just less than. It shades below. What if I intersect a couple of these things? What's it going to look like? let's intersect. We'll officially get to this later, but we just happen to have this thing up there. So let's make that greater than or equal to, and I'm gonna do less than or equal to. Let's just do the quantity x minus 2 squared plus 5.
Where did that song even come from? Now it's just stuck in my head.
There's the first. There's the second. Alpha shades 1. Oops, what is it? This thing skips. It really is kind of goofy that way. Alpha shades 1. There's first. There's the overlap with the second. Right?
Good video.
It's not lines anymore.
How would that apply to data? Like
Well, I mean,
like in bio, like code that like biology.
if there are limited, like if you know that the number of bacteria has to be greater than this threshold or something. You know, I mean, we'll look at some example problems. Okay, let's get out of here though. I'm gonna show you some of the features. How much time we got? We just down a couple minutes. 10 minutes, yeah, that's good. So we might as well not go down there anymore. Let me get out of here. Oops. Okay, so let's go ahead and just let's turn this one off and we'll just use this one. How about? Turn that guy off. If I go zoom 6. Okay, there's my parabola. This is kind of handy. If I want to find the coordinates of a vertex graphically, there's a way to do this on your calculator. You can ask it, if you go to the calculate menu, which one do you suppose would do it there? Not intersect.
Value.
Minimum. Minimum is going to work because if we go back to the graph, a minimum just means the lowest point on a function, right? A valley. Well, if it's a parabola that opens up, the minimum is going to be that lowest point of the valley right there, which turns out to be the vertex, right? The vertex for a vertical parabola is always either going to be, if it opens up, it's going to be the minimum. If it opens down, it's going to be the maximum, the top of the peak, right? And so I can always use those two features on the calculator. Have I showed these to you? I can't remember if I have. I don't think, maybe last year, but I can't remember. So we do minimum, and then what it's going to ask you, the criteria the calculator wants is a left boundary, a right boundary, and a guess. And so what that means is if this is the point that we want to know about specifically, I just have to pick a point on the left of that and a point on the right to narrow down the range where the calculator has to search. And then the guess, I don't know why they even include a guess. It's kind of weird that they do, but the guess has to be just some point in between. The closer you get, the easier it makes it for the calculator, right? But not that it's hard either way. So that would work for a left boundary right there, wouldn't it? I can either trace over, or I can see that x equals 1, 2, 3, 4 would be a good choice for the right boundary. So rather than trace, I can just hit 4, enter, and it puts the right boundary right there. And for my guess, I'm going to say, well, I'll just trace over a little bit. That's close enough right there. Enter. And it tells me the coordinates are 1.999999992. What's it really trying to say? 2. Yeah, and that's not weird that the calculator, it doesn't come up with, a lot of times, the exact right numerical answer, because the algorithms that it uses, like it uses, for example, Newton's method and some things to try to find that place where it's at a minimum. It goes through a complicated set of algorithms, and sometimes there's just some rounding error in there, because the calculator can only carry so many decimal places in its calculations, and sometimes that adds up just a little bit. You get these numbers that are slightly off. But you just learn, as you use this thing, you just get used to just ignoring that and saying, well, it just meant 2. Okay. Make sense? Okay. There's another way to do that, that's, I think, maybe a little more accurate. If you know that the parabola opens up, if you go to the math menu, you can come down here to number 6, function minimum. Because you know it's gonna be a minimum, right? For function minimum, all you have to do is plug in, first you plug in the function. So in this case, it was, remember what it was. I wonder if I can put in y1. I might be able to. Let's try that. If I go alpha f4 y1, normally you would just put in the function in terms of x. So whatever it was, the quantity x minus 2 squared plus 5 is what I think it was. You put that in there, then you put a comma. It needs to know what's the independent variable, x, right? So x is the horizontal variable. And then I want to look between what two x values. So we could say, I wonder if you have to put that. May not even need to. Let's try it without. I can't remember. Argument, go to. Okay, yeah, it does need something. It needs, look between, say, 0 and 5.
Interesting.
That's not right.
No, cause we used Y2.
Yeah. Oh, it was y2. You're right, yeah, it was y2. No
Y1
wonder.
turned off.
Okay. So if I go back, that's right. So it is gonna work though, I think, with the y1. So we'll just make that alpha f4 y2, oops, y2. Now let's try it. Yeah, it worked, see? Okay. And if I wanna know what the y value is, I just plug that back into the function. But probably the graph is easier, huh? Does that make sense?
What was 0 and 5 supposed to represent?
Okay, those were just look between, it's guaranteed to be between those values, so I'd have to kind of know
Those be values of x and y or what?
X.
X.
Yeah, so that's a left boundary and a right boundary. Okay, make sense?
Let's see.
Okay. All right, I don't get any more. That's good.
Not even there.
Okay.
Maybe, depending upon when the bell decides to ring.
No, there seems to be, my phone dead on with the bell.